So this video is going to teach you the basic principles behind a series circuit and how to analyze it using Ohm's law. However, if you get through this and it doesn't make a whole lot of sense to you, feel free to search up series circuits on YouTube. You'll find 100 more coming from different perspectives. We're using slightly different terminology. It might make it a little bit easier. So what I've drawn over here is a series circuit. We have a battery with 6 volts of potential energy. We have one wire coming out, and we have 3 different resistors it's going through. And over here I've drawn Ohm's law, but I wrote it in 3 different ways where I isolated a different variable each time. So sometimes we need to rearrange it to fit what we're trying to do. Now what makes this a series circuit is there is a single pathway from one end of the battery to the other. Okay, there's not several branches where the electricity can flow through different spots. All the electricity, all of the current must flow through all 3 resistors in order to get from one end of the battery to the other. Okay, so that's what makes a series circuit special, is it's one single pathway. Now there's some special things you'll recognize about this once you get used to series circuits that are always the same in each one. Okay, I want to go back to our earlier description of how these things are kind of like squeezing a tube of toothpaste. This 6 volts is like the squeezing pressure. We're squeezing a tube of toothpaste, and there's a certain hole where that toothpaste can come out. Now, that hole is dictated with toothpaste by the diameter of how big that opening is. But that's what these resistors are. The more resistance you have in a circuit, it's like squeezing and constricting that down to a much smaller hole. So even though you're squeezing with the same amount of pressure, only so much toothpaste can come out. Now, if I were to squeeze with 6 volts of pressure, and that doesn't make any sense the way I said that, but a certain amount of pressure I'm squeezing with, and I don't change that amount of pressure, and I have a fairly constricted hole where it has to go through a very small opening, then what you'll find is that the toothpaste comes out slowly, but the toothpaste doesn't speed up in different spots. It's not like it gets out and then starts going faster. It's all constricted down at the same amount. Okay, it's all constricted by the same amount, and so it's going to flow out at the same rate all the way around. We're going to see the numbers show that. Okay, now the first thing we're going to take a look at is when you have more than one resistor, we need to find what's called the equivalent resistance. We need to basically say, if we're the battery, what do we see out here? The battery can't tell there's 3 different resistors. It only feels a certain amount of squeeze or restriction on how much current can come out. So we want to know what's that overall total. Now with a series circuit with only a single pathway, it's very easy to calculate this. The equivalent resistance is just going to be R1 plus R2 plus R3. And I can keep going on and on for however many resistors are in that single pathway. So in our situation, we have 2 ohms, 1 ohm, and 7 ohms. So it's 2 plus 1 plus 7, which would be 10 ohms. So our battery, if it could see what's going on, it doesn't really care what's out in the circuit. It has this certain feel, like how much restriction is there on the current that can come out. The battery, for all it knows, the circuit looks like this. 6 volts, 10 ohms. Okay, so from the battery's perspective, this is all that it's really seeing. We know there's 3 separate resistors, but it just feels 10 ohms of resistance kind of restricting and squeezing down how much current can actually come out. So this is what the battery kind of sees from its perspective. Now, what we're going to do with this is we're going to analyze what's happening in each spot, because series circuits have certain features that are always kind of the same. So the first thing we're going to do is we're going to figure out how much current is coming out of the battery, and we're going to use this as our guide. Okay, so if I look up here at my formulas, current is equal to voltage times resistance. So the current coming out of the battery, I want to put battery down here. So the current that's coming out of the battery is going to be equal to the voltage on that battery, 6 volts, divided by the overall or equivalent resistance of 10 ohms. And when I divide those, I'm going to get 0.6 amps. Okay? Now that means at this point, there's 0.6 amps of current coming out of the battery. And at this point, there's 0.6 amps of current coming back to the other end of the battery. And what we'll find is, no matter where we go in this circuit, it's only a single pathway, everything moves at the same rate. So we have 0.6 amps everywhere. Okay. So one of the things we can definitely say is the current is constant. Okay, the current is the same everywhere for the entire pathway because there's only one pathway. So that's special for a series circuit. Now, what we're going to analyze from here on out is we're going to take a look at each of these resistors. They're all different amounts of resistance. We have 1 ohm all the way up to 7 ohms. Now, if you think about it, this is a certain amount of potential energy over here. And that potential energy is going to get divided up and used differently in different spots because it takes more energy to shove something through a small hole or to shove something through a place with lots of resistance. It takes a lot more energy to do it here than it does over here. This has minimal resistance. So this 6 volts of energy is not going to get divided up evenly, but it will get divided up based on the amount of resistance at each spot. So the way we figure this out, we call these voltage drops. If we're going to find the voltage drop across R1, that's this one up here, that means how much potential energy gets used up, so to speak, or sort of allotted to that specific component, whatever it is. How much of it is just for that spot? How much of it, and we call it a voltage drop, how much does the potential energy decrease after it has to push the current through this particular opening, for lack of a better term. Okay? And essentially that means the power to that component, whatever it is. So the voltage drop across to R1, I'm going to look up here, and voltage is current times resistance. Well, I know the current is 0.6 amps everywhere. So my current is 0.6 amps, and that's going through a 2 ohm resistance. Okay? And when I put that together, I get 1.2 volts. So what we're saying is 1.2 volts. That's how much of this 6 volts gets used up along the way in order to power that component. Okay, we call that the voltage drop across R1. Now let's do the same thing for the voltage drop across R2. We have 0.6 amps everywhere in that circuit, but now it's only going through 1 ohm resistance, and that's going to be 0.6 volts. We'll take a look at our third component. The voltage drop across R3 is going to be 0.6 amps. But this time it's going through 7 ohms. It's going to take a whole lot more energy to push that current through that amount of resistance. So I put 7 ohms right here. And when I plug that into the calculator, I get 4.2 volts. Now what we see is these are the voltage drops across each resistance. What that really means is, where does this 6 volt go? Okay, most of the energy from this gets used up on R3, some gets used up on R1, and a little bit left for R2. It gets divided up, but not evenly, because not all these resistors are the same. If they were all the same, it would all get divided up exactly even. If I add these together, I should get, now I may, on some of these amounts, you might round a little bit, and so you're just slightly off. Don't worry about that, but you should get close. If I add this up, I should get 6.0 volts, which is my total amount of voltage on the battery. So what we were able to find is we were able to find the equivalent resistance. We use that to find the total current, and that's going to be the same everywhere in that. But the voltage gets divided up amongst each component, and that should equal the total voltage on the battery. So the main things for a series circuit: the current is constant, the voltage is divided. And remember, it's not divided evenly unless these are identical resistors.